Chapter 6.3 Energy Changes and Conservation of Energy. In this chapter, you will learn many daily examples of conservation of energy, and in particular, the conservation of mechanical energy. 1. Conservation of energy. Last year, you have learned how to solve problems of mixing in the topic of heat. When hot liquid mixed with cold one, there is conservation of energy. Energy released by the hot object is absorbed by the cold object, if there is little heat loss to the surroundings. Similarly, kinetic energy and potential energy also interchange in many common examples. For trampoline jumping, as in figure 6.3b, the girl starts from a maximum speed, 8 meters per second, and then she rises. As she rises, she slows down. Her gravitational potential energy increases while kinetic energy decreases. She reaches maximum height when all her kinetic energy becomes gravitational potential energy at a height of 3.26 meters, where her speed is 0. If we take the gravitational potential energy at the trampoline level to be 0, her gravitational potential energy, Gpe, equals mgh. So, a plot of Gpe against height h should be a straight line through the origin, as in figure 6.c below. Her kinetic energy, on the other hand, decreases as her Gpe increases. So, the kinetic energy is another straight line, the blue one, which has a negative slope from the beginning of the motion to the highest point. And the sum of Gpe and Ke is the total mechanical energy, which does not change due to conservation of energy, as there is no energy loss to the surroundings. And there's a graph on the left that you should also take attention. This is a graph of energy versus time. And from the two relationships, especially the one for kinetic energy, you can see its relationship with time t, that it should produce a curve, which should curve upward this way. By the way, the total mechanical energy, which is the Ke plus gravitational Pe, remains unchanged all the time. 2. Examples. Sum of Ke and Pe constant. Let's look at other examples to see how Ke and Gpe interchange. In example 6, a gymnast throws a hoop. The hoop starts with an upward velocity and hence a kinetic energy. Then the hoop rises until all its kinetic energy changes to Gpe. Hence, half mv squared equals mgh, which gives h equals v squared over 2g. In that way, we may calculate the maximum height. At other height, we may also find the speed of the hoop by first calculating the loss in Gpe, which becomes kinetic energy at that height, so that we may find the speed of the hoop. A. Simple pendulum. You have seen simple pendulum on page 5. A simple pendulum performs a motion in which the acceleration is not constant. The acceleration of the mass is higher when it is further away from the vertical, the equilibrium position. As the pendulum swings from one side to another, the gravitational potential energy and kinetic energy interchange periodically. It has a maximum speed when it is at the lowest position, and hence a maximum kinetic energy there. Its kinetic energy changes to gravitational potential energy as it rises to one side. At that time, its speed becomes smaller and even finally a rest when it is at the highest point. At that time, the Gpe is a maximum. Experiment 6a. Energy changes in a simple pendulum. The experiment verifies the conservation of energy for the simple pendulum. And let's take a look.
Put the 0.5 kg mass to one end side, raising it through a height h. above its lowest position. Measure the height h. Start the ticker tape timer and release the mass, allowing it to swing to the other side, pulling the tape with it. Examine the dots on the tape.
The experiment verifies the conservation of energy for a simple pendulum. The maximum kinetic energy of the pendulum is calculated by the measurement of maximum speed at the lowest position using ticker tape. The maximum gravitational potential energy of the pendulum is found from the initial height h of the mass. The results agree with each other with acceptable experimental error, and so we prove that there is conservation of energy. For all the above cases, there is no energy loss during the motion. The total mechanical energy does not change. And since GPE equals mgh as usual, a plot of GPE and KE against height for a simple pendulum will also give the same graph as in figure 6.3c. In example 7, a light gauge is used to find the maximum speed of a swing. The maximum kinetic energy is found and the highest height estimated. Well, the sphere finally cannot rise so high as expected. Do you know why? There is an experimental difficulty that is difficult to overcome. Take a look of part C. If you would like to try this experiment in class, ask.